for a moment there. So there's a non-profit organization called H Plus, or Humanity Plus, which is a U.S. organization which is kind of oriented toward discussion of future technologies and their implications, which puts on conferences from time to time, including, we did one in Hong Kong, and so now, due to being here for the AGI conference, we're having the Humanity Plus conference in Beijing, which is, in fact, tomorrow, so at the Jintai Art Museum in the Chaoyang district. So that, I'm not really the main organizer of it, but I help recruit many of the speakers who will be speaking there, which includes myself and Cosmo and Yi Ching, who has disappeared, and as well as Hugo de Garis, who is another AI guy who lives in China, in Xiamen now, and James Newton Thomas, who works on AI for intelligent minds in Australia. So there'll be a fair bit of overlap. I mean, with the kind of topics we're discussing here. The price of admission is like $15 US or something, so it's inexpensive. And I actually have no idea how many people we're going to get for the conference. The room may be as empty as this one, or we could get like 100 people. I don't know. I mean, we pulled in, as of a week ago, this group called Beijing Commons, which organizes the bar camp and TEDx and a bunch of other things here. And they have tried to recruit some of their people to come. So we'll see how it goes. I guess in the prior AGI conferences, we've had a day at the end of the conference, kind of the future of AGI workshop, which is more speculative about the implications of AGI and so forth. And this year we didn't do that, but we're doing the Humanity Plus Beijing kind of the weekend before the AGI conference, which is a sort of similar themes. In any case, now they keep calling me with things like what kind of how much food should we order for the conference and so forth, which I have no idea. Right? So, yeah, as many of you as have free time on the weekend, it'd be great to have you there. I think it starts at 9 a.m. at the Jintai Art Museum, but if you don't get up in time, you can show up a little later. Nobody will mind. Right. Many similar.
I think it starts at 10 a.m.
Is it 10? Did they change it? All right. That's good for me. Yeah. Let's see.
It says 10 a.m.
Oh yeah. Cool. I wonder when it ends now. Well, there I am anyway. Yeah. Adam Ford, Hugo de Garis. There's Yi Ching. All right. I didn't know she played the violin. All right. Oh, they left off a speaker because we didn't have his picture, I think. Yeah. That's okay. Yeah. So, we're going to do two things this afternoon. One of them is to continue our discussion of OpenCog and its foundations. And the other is, for those who are interested, to install and run the large unwieldy beast that is OpenCog. Lake will be on hand to help you do that, and Cosmo can probably lend a hand too, since he's already gone through that process. So I think in terms of the installation of OpenCog, so on Monday, Lake is going to demonstrate OpenCog connected to the Unity game world for controlling a video game character, and go over that aspect in some depth. And that involves having to run that yourself, involves having OpenCog installed and also involves having the Unity player installed and getting the networking to work between those. But having OpenCog itself running on your system is valuable for other things besides the Unity game world anyway. But I would say at this point in time, like the OpenCog system doesn't do anything extremely amazing or exciting unless you actually want to be doing research and development involving it. I mean, if you want to use Moses to classify data sets, or if you want to work on developing PLN or test out attention allocation and see how it works, if you want to participate in OpenCog research and development, it's certainly a prerequisite to install and run the system and understand the details. On the other hand, if you're probably not interested in kind of hacking in the system and trying to make it smarter, once you install it, it's not going to be very exciting. I mean, you can load some data in and query the atom space, and you can spread attention and do some simple things. But there's no exciting whiz-bang demo as of this point in time. I mean, the demo of controlling the agent in the virtual world, as Lake will walk you through on Monday, it's meaningful and it's worth seeing. On the other hand, if you're not going to be trying to improve it and playing with it, probably running it on your machine isn't that much more impactful than watching Lake run it. So I'm definitely not trying to talk you out of installing it. I'm just trying to set expectations realistically. I mean, it's an in development research system. It's not a video game in itself or an exciting system to play with, except for the excitement of making stupid AI code get slightly smarter through your own efforts, which I find exciting. So, yeah, for those who want to get OpenCog running on your system, I think Lake has a couple USB drives, is that right?
Yeah.
Which have all the different dependencies and everything that's needed to run OpenCog on them. So the best thing to do if you want to run OpenCog is get the USB drive from Lake and copy it onto your system. That would be step one. So, yeah, and that, since it takes a while to copy stuff from a USB drive, this will be a somewhat serial process. But then following the tutorials to get it running, of course, people can do it in parallel. So actually, while I go through a bit more of lecture and discussion, perhaps we could get started with that. So who is interested to install and play with OpenCog? All right, so we have, Cosmo already has it. So we have those people. So you might as well distribute the USB drive and get started with that.
One thing I think we should do as well is let's put up the web address for the start of the tutorial.
Yeah, sure.
So that they can go through that on. There's a part in the tutorials where it calls for a USB if you need it or desire it.
Okay.
Because if you already have like the Ubuntu system, then really you don't strictly need a USB, especially if you're internet connected.
But it's not.
Yeah, it's not. Right? So
Well, it's not here right now. That good, actually. Yeah.
It's not OpenCog.
Oh, I don't know. What is it in?
It's the Beijing 2013 tutorials. Yeah, there you go. Okay, so this is the start page for the tutorial.
Yeah. So for those who are interested, if you I just Googled OpenCog Beijing AGI Summer School 2013, but You see the URL up there also.
Okay, and who would like a USB? I'll put one on the left. I guess can pass it around. Get it back to me. Down. If you have a question,
So what?
slide it down.
So among the people who are going to be installing it, how many are running the Windows operating system? How many are running Ubuntu? How many are running OS X? That's too bad it doesn't work. Well, I mean, we're doing Ubuntu virtual machine. In theory, OpenCog almost runs on OS X, but there's been various nitty-gritty dependencies that we didn't quite work out. I mean, there's no strong reason it can't be made to run on OS X. We just didn't quite work through everything, I guess because it's easy enough to run an Ubuntu virtual machine. Yeah.
What's better, Ubuntu or Windows?
That's a philosophical question. No.
I'm just running because
Yeah. So that's actually a complex question. So for OpenCog itself doesn't run on Windows. So if you have Windows as your base OS, you'll run OpenCog in a virtual machine. Now, the Unity game engine that we're using for the video game world, the Unity game development environment only runs on Windows. However, there's a Unity player that runs in Ubuntu Linux. So possible scenarios are as follows. If you have Windows as your base OS, then what you'll be doing is running an Ubuntu virtual machine with OpenCog on it for OpenCog, and then Unity in Windows, and then they'll network between each other with sockets. Now, if you have Ubuntu as your base OS, what you'll be doing is running OpenCog in Ubuntu, and then running the Unity player in Ubuntu. Now that has the downside that you can't do Unity 3D development, but in the scope of this course, we're not going to be doing Unity 3D software development anyway, so it really doesn't matter. So eventually, Unity will have a development environment in Linux. They say so anyway.
Yeah, well, they say at some point in version 4, we're at like 4.2 now. So
Yeah, but it hasn't happened yet. So yeah, I think you have like a dual boot on your machine there.
yeah, dual boot. I would say go with Ubuntu.
okay.
Yeah, sure.
Yeah, I mean it's probably easier. Just
Yeah, there's less risk of networking issues between the game world and OpenCog if they're both running on the same OS. So, yeah.
Okay. Cool. Yeah, Ben mostly covered it, but
Could you explain the demo? Could you explain the different elements that is in the demo?
I'm going to go over the demo itself more on Monday, but I'll just say that if you follow this tutorial, you'll see that you need to install the main OpenCog repository on your machine, and you also need to build the embodiment server and download one of the players for Unity. Those are the three main steps. So.
Could you explain the embodiment element?
Sure.
Because
Embodiment code is in the greater OpenCog repository. Once you've downloaded the repository, you have the code for embodiment. There's a step where you will build the embodiment server from the code because you need to run it to do the demo. So at that point, you'll basically, where it says setting up embodiment on the OpenCog side, 3.3. So yeah, you basically just make it, or CMake it. And then once you've built it, you just do this start embodiment shell script, which starts the embodiment server. I'll go into some details about what embodiment is a little bit later. I didn't want to necessarily take up Ben's time now when he's talking about stuff, but these tutorials are pretty good. And if you have questions, I'll put my email and Alex's email up there so that you can send it to us if you're still trying to work on this tonight or something. So, Alex wrote the tutorials, I just do the game stuff. Alex's?
Is there a dot between your names?
There's not. Sorry.
It's okay.
For argument, it's not.
Ah.
Okay. Cool. We wanted to start with the tutorials today, or getting people installed, just so that to make sure we had everything ready for Monday, since it might take long.
Yeah, I mean, most of the time it's unproblematic, but every now and then, if you have some old version of some library in your system or something, something can get confused because it's complex Linux system with a lot of different dependencies. So yeah, the hope is to work, if there are any issues today with just getting OpenCog to basically compile, link, and run on your system, those can be worked through today, so that then when on Monday Alex goes through the game world stuff, we can just deal with running the game world stuff rather than with linking and operating system issues. So, where should we go next? So yeah, if you have any issues, we're going through that stuff. You can pester Lake. He's sitting back there, eager to be pestered.
Turn around and point or something.
Did you find any Slurpees, by the way?
I did not.
So then, I mean, the other thing to add on that is there's nothing secret on those USB drives, so if you don't happen to do that in the class today, if you follow the instructions on that page at home or over the weekend or whatever, we were just talking about you.
Really? I hope it's not all bad.
It's confidential. Yeah, I mean, you can always at home go through the instructions on that wiki page, and it just involves downloading stuff and installing stuff. It's fairly straightforward, although now and then something weird happens. If anyone wants to make it compile and run on the Mac, that'd be great too. I don't think it's that far off. David almost got through it, right?
Yeah, and the Unity stuff does work on Mac.
Yeah, that's right. What's that? The scheme shell works? What doesn't work? Significant parts work. So that's the only part you need to use. Right? Yeah, so for basic experimentation with the NLP system, it works on the Mac. So now I will continue running through the multitudinous components of OpenCog. Actually, there's only two big components left to go through. Then there's a bunch of other smaller things that I'll mention. So one of the big components that's left is Moses, which is the automated program learning algorithm, which is quite complex, and I've been doing a lot of work on in the last couple years. And another component, which is quite important, although not much has been done to the code base in the last few years. We're about to start using it a bunch in the context of this game world, is attention allocation. So this has to do with how does attention spread around this large network. And I mentioned before that every atom has short-term importance and long-term importance values associated with it. So what this tells is basically how the short-term and long-term importance values spread around through the atom space. And this is roughly analogous to how activation spreads around in a neural network. I mean, not identical, because it's not modeled in the brain, but it's a similar concept. You're spreading importance tokens around. So the mathematics we use for the spread of attention around in the network is based on the idea of virtual currency. Like each atom has a certain amount of money, and then it spreads that money around to the various other atoms. So because of that, we've called this an economic attention network. And the primary use of the economic attention network is resource allocation. So the basic idea is that the different mind agents that are acting on the atom space and that are being repetitively scheduled through, many of these mind agents don't operate on all the atoms in the atom space. Instead, they pick a handful of atoms and act on those atoms. So you have a PLN inference process, for example, that's not going to do inference on everything. It's going to grab a few atoms out of the atom space, do inference on those, then put the results back in. So when a cognitive process, a mind agent, grabs a few atoms out of the atom space, how does it choose which atoms to grab? And a mind agent could do that however it wanted to, in principle, but in many cases what it will do is choose atoms with a probability proportional to their short-term importance. And actually, I learned recently that the API functioning enabled that had been eliminated, and we're now replacing it. You saw that on the OpenCog list. So. But that's an important element, to choose a random atom with probability proportional to short-term importance. And the reason that means something is because we have this economic attention network process spreading importance values around. So when one thing is important, other related things may become important after that in the classic manner of association spreading. So the ECAN network, it's basically just a way of looking at the atom space. We have nodes and links, and we have two special link types, the Hebbian link and the inverse Hebbian link. And actually these can be either symmetric or asymmetric, so actually there's four. Basically the Hebbian link means when one node is active, another node tends to also be active. An inverse Hebbian link means when one node is active, the other one tends to be inactive. And then that can be asymmetric, meaning when this guy is active, this guy is inactive. Or it could be symmetric, meaning whenever one of these two is active, the other one is active. And the inverse one could also be symmetric or asymmetric. Now what makes things subtler is that sometimes the attention allocation module will interpret other link types as if they were sort of virtual Hebbian links. Because, I mean, if you have an inheritance link or an evaluation link between two atoms, in a way that means those things are associated. I mean, it means there's a probability greater than random that when one of those links is active, the other one will also become active. But these links just exist to record associations, and they're much like the links in a Hopfield neural network. If you work with a Hopfield attractor neural network, in that network, the link between two nodes occurs by Hebbian, its weight is adjusted by Hebbian learning. So if you have two neurons in a Hopfield neural network, and these two guys are active at the same time, then the weight of this guy gets incremented. If this guy is active but that guy's not active, the weight of this guy gets decremented, right? And in a classic Hopfield net, that's done symmetrically, but you could also do that asymmetrically, and you get an asymmetric Hopfield net. And I worked a bunch with that kind of neural net in the late 80s and early 90s. I mean, they're quite interesting. You can get all kinds of complex attractor patterns emerging in them. And in theory, you could represent any kind of complex knowledge in that sort of neural net. However, the route we've chosen in OpenCog is to use this kind of neural net largely to allocate attention in a network which is a kind of neural symbolic hybrid network. And rather than having a single activation value, we have STI and LTI values that propagate around. And these links are weighted with probabilistic truth values. They're weighted with probability values, just like most other atoms in OpenCog. So STI and LTI in the system now are treated as two separate artificial currencies. There is a theory by which you could convert between one and the other, but we're not actually using that in the code. In the code right now, they're like two separate kinds of money inside the system. And calling them money, the main thing that means is that they're conserved. Like the total amount of STI in the system can be considered constant in most cases. The total amount of LTI in the system can be considered constant in most cases. And this is different than a neural net. Like in a neural net, the total amount of activation is not constant. I mean, there's energies coming into the neural net, and then it spends that energy by shooting out activation. But you don't have a conservation of activation. If you think about how a typical neural net works, the neuron has a certain threshold, right? So it has some inputs, and it accumulates its input up to a certain level. Then when the input crosses some threshold, it fires, right? But the amount that it fires is not proportional to the amount of input it got necessarily, right? So you don't have a conservation law. I mean, you might have some approximate conservation law in a mean field theory of the neural net or something. But saying you're dealing with artificial money is a bit different. Now, of course, you could break that just like real governments do. They say, well, hey, I thought money was conserved, but now we're going to print a few trillion more dollars like the U.S. government, right? So you could do that here too. You could create more STI or LTI currency. Right? Now, the concept is the STI is the immediate urgency of the atom. Like how useful is it to pay attention to that atom? The LTI is how important is it to have that atom in RAM, basically. And I mean, in some of the papers on this, we express that more fancily in conditional probabilities. I mean, this is like the SGI has to do with the probability that paying attention to the atom will bring utility in a short time frame. The LTI is the probability that paying attention to the atom will increase utility in a much longer time frame. And when you look at it that way, you see it's kind of arbitrary. Really, you could have a whole utility distribution, right? You could say, well, here's for each particular atom, here's time, and here's how likely is it that paying attention to the atom on this time scale is going to be useful, right? So then say for information about this room and this building, for me, like over the next 1 week, remembering where this building is pretty useful. And then after a while, it becomes not useful at all for me to remember where the details of this building. On the other hand, say, for example, what my mother's house looks like, right? This week, I don't care what my mother's house looks like at all. I could save that to disk. However, in the longer term, there's some reasonable value to me. I don't know exactly what it's going to be because I don't know when I'm going to visit the U.S. where she lives. I know I'm not going to visit there this week, so it's pretty low. But in the longer term, the utility of knowing where my mother's house is some kind of low but constant level. Whereas knowing the geography of this building is quite useful now, then almost useless in the long term. They're not entirely useless. So you could look at this sort of distribution over time. You could look at this sort of distribution over time as a continuous thing. Oh, you missed our discussion of deep learning this morning. Too bad. Yeah, we did hierarchical temporal memories and so forth. Yeah, it was great. I mean, we revealed the secret to immortal life and superhuman thinking machines. But we're sworn to secrecy now.
I'm ashamed, but I was ill, sorry.
That's all right. I was quite late too, actually. Yeah, so this, however, keeping the whole utility distribution for each piece of knowledge, as well as being hard to estimate, will be expensive to retain. So similar to the reason why we don't retain a complete like probabilistic truth value distribution for every truth value. Here we just kind of say, okay, short term, long term, right? And okay, two numbers. And these two numbers are a compact, hopefully not too terrible summary of a whole distribution of the expected utility of knowing something at a certain point in time. Now, having two numbers happens to match fairly well with the von Neumann computer architecture because this one has to do centrally with processor, this one has to do centrally with RAM. This is like, do you kick it out of RAM or not? This is, do the mind agents pay much attention to it? So it's again a simple approximation, but if you're trying to build something that's going to work on a very large network of nodes and links, what you need is a simple approximation, right? And then forgetting, basically the simplest kind of forgetting is when RAM gets full, just kick out the things with the lowest long-term importance values. Now, that's actually not the best heuristic. You could certainly cook up cases where you have like 100 things and you just need to remember one of them, right? So then just killing the lowest LTI thing isn't good. You need to do some reasoning about which of these things can you afford to forget, especially when you consider you could fish things back from disk, right? So in that case, like, let's say I had 20 friends from first grade. I don't need to remember what town they all lived in because I know they all lived in the same town. So if I just remember the town one of them lived in, I'm okay, right? So there's plenty of subtle cases where just forgetting the lowest LTI things is not the best heuristic, but that's what the code does now. it forgets the lowest LTI things. And I don't think the human brain has particularly better heuristics for what to forget. I mean, I remember a lot of things I would rather forget. And I mean, I remember a lot of useless things. And I've forgotten, for example, the Spanish language that I used to sort of know. I've forgotten many things I would rather remember. So I think that this is an area where exceeding the human level may not be terribly difficult. Yeah?
Is there any relationship between the STI and the LTI? For example, the LTI must be at least the STI?
Nope.
So they're completely independent.
At the moment, they're independent. Yeah. I mean, you could convert between them to some extent using inference, because I mean the probability that's useful in the near term isn't really wholly independent of the probability that's useful in the long term, but it's fairly close. I mean, kind of like in finance, the one-day return is almost independent of the one-week return, but not quite, but they're almost independent, just because the world is complicated. Right? So yeah, in theory, there's some dependency, and in theory, there's more subtly forgetting than to forget the least important things. And you know, there's a lot of trickier stuff you could do too. Like something isn't necessarily just important. It could be important for one reason and not for another. It could be important to reason about, but not important for any kind of perceptual learning process or something. So you could have mind agent specific importance, or conditional importance. This is important until I found out this thing, and then after I found it out, it's not important. But at the moment, we've opted for simplicity and just have these two numbers on each atom and then propagate them according to certain equations. So we have the notion called the attentional focus, and this was actually a major architectural decision in building OpenCog. So there's a notion in psychology of the long-term memory and the working memory. I mean, the working memory used to be called the short-term memory. Now psychologists don't like that anymore. They like the working memory. And the working memory, as conceived in modern psychology, has a host of different subsets. There's like a subunit used for kind of perceptual rehearsal, several subunits used for linguistic priming, and there's a lot of debate over what all the subunits of working memory are. But it is pretty well demonstrated by experimental psychology that working memory and long-term memory are not identical. And there's the classic result that the short-term memory in humans has a capacity of like 7 plus or minus 2, which has certain caveats associated with it, but it's still kind of interesting. Like, by and large, in most contexts, you can't remember like 550 things in your mind's eye at one time. Probably not even 25 distinct things, unless you're autistic or a certain kind of super genius, right? But 5 or 6 things, definitely. So this is the magic number 7 plus or minus 2. What's interesting, I read it seems to hold for mice as well. Okay, I would have thought they'd be like 4 plus or minus 2 or something, but it seems a more general thing of the mammal brain architecture. Right? But I don't think that has to hold at all for an OpenCog system, right? I mean, the whole notion doesn't quite make sense for a computer with the current architecture, because that can just remember a very large number of things at ready access at any point in time. But in terms of building an AGI system, one choice you can make is make separate components in your system for a working memory and a long-term memory. And in OpenCog, we haven't made that choice. Instead, we view the atom space as this whole big cauldron of activity with nodes and links being acted on by a bunch of different mind agents, and among other things, spreading activation among each other, which is done by some attention allocation mind agents. And some of these are more important than others. And basically, if you rank the atoms in the atom space by STI, the atoms with the STI above a certain level, which is the attentional focus boundary, the atoms with STI above that level, basically we consider those are the working memory. So in the OpenCog architecture, the working memory is just the most important stuff, basically. And that's an architectural choice which is different than separating working memory and long-term memory. And I think NARS and ERA essentially make the same choice, so it's not that controversial a choice. LIDA seems to make a different choice. I mean, in LIDA, the working memory and long-term memory are like separate Java objects. They're not the same thing. So, and in the brain, it's kind of a little of each, I think. I mean, in a sense, the working memory uses a lot of the same parts of the brain as long-term memory. It's kind of a distributed attractor pattern, but yet there are particular parts of the brain that are consumed solely with working memory. And if you have a lesion in those parts of the brain, your working memory can be screwed up, but your long-term memory is fine. So this approach, we kind of hard code a value, which is the attentional focus boundary, and the things with short-term importance higher than that are treated a little bit differently. So that some parameters of the equations that spread the attention values are different for things in the attentional focus and things that aren't. But I mean, it's all one atom table, right? We don't have a separate attentional focus atom space. And then you can interpret Hebbian links in a kind of simplistic way, like if two things are both in the attentional focus, you build a Hebbian link between them. So the equations that update the importance values, and there's similar equations are used independently for short and long-term importance. So we can, with different parameters, because short-term importance basically decays faster. So we can, short-term importance decays faster, long-term importance decays quite slowly, but the basic update equations are similar. So we can think about the equations this way, like each atom has a certain amount of STI currency, a certain amount of STI money, but periodically, each second or something, it has to pay a little bit of money in order to stay in the attentional focus. So each thing in memory has to pay a little bit of money to stay in memory. And eventually, if it didn't get any more money, it would pay so much money, it would get kicked out of, short-term importance would go to zero, and then nothing would ever pay attention to it, right? Now, how does it get money? Well, it gets what's called stimulus values. So when a mind agent, this could be reasoning, could be Moses, whatever, when a mind agent uses an atom for something, so say you're reasoning cat is an animal is ugly, therefore a cat is ugly. So then cat, animal, and ugly, those nodes, would all get some stimulus. And the stimulus value is then periodically converted into what are called wages, which is money that's added on to the STI value of the node. So the reason stimulus is there is for normalization. So basically when an atom is used, it gets stimulus. Then after a certain period of time, the stimulus that created each atom is added up and normalized by the total stimulus. And then the amount of currency is given proportionally. So the conservation of currency is done by normalizing stimuli into wages, which are based on how much money the central bank, which is associated with the COG server, which is the software object that holds the atom space and the mind agents. So we view this, the basic OpenCog cog server, as the central bank, and it gives out wages and collects rent, and that's the essential dynamic. And then there's a important spreading agent that mediates that process. Now, to stay in the attentional, if you're here in the attentional focus, that's like having an apartment in Hong Kong Central or something. You pay extra rent for being the attentional focus. On the other hand, the benefit of being the attentional focus is that many mind agents will preferentially choose things that are very important, and plus you'll get more Hebbian links built when you're up there, and then get more activation spread. So if you don't charge more rent to things in the attentional focus, what you get is a rich stay rich dynamic, where some things get in the attentional focus and they spread activation among each other, and it becomes like the US economy, where you have a bunch of rich guys spreading money among each other and everyone else stays poor, right? So, but if you charge more rent to the rich guys in the attentional focus, then there's something that's pushing them out, which counteracts the kind of self-reinforcing dynamic of everything staying important. So there's, yep.
Does that mean to say that if the AGI finds itself in a completely different context, it will completely swap out its attentional focus to something else?
Yeah, that's right. You think of it as like a moving bubble of attention. It's like this is whatever seems most interesting in the moment. And these are experiments we should do hopefully in the next few months in the context of the game world. Like the agent is wandering around among some trees, and it's say there's a bunch of hot dogs down there that give it energy. While it's walking among those trees with the hot dogs in the game world, its focus is on trees and hot dogs. But then if it gets away from that area and climbs up into some building, now there's no more trees, no more hot dogs. It should start thinking about, it should stop being obsessed with those things. It will start thinking about other ways to get energy. Then it will be more open to, say, opening a hidden door to get energy or something. Now, it's easy to simulate certain human pathological, psychological states this way. Like you can get an obsessive compulsive system really easily. I mean, it's just, if you just don't charge extra rent for being the attentional focus, you'll get an obsessive compulsive system. Because it'll just keep thinking about the same shit over and over and over and over again. On the other hand, if you set the penalty too high, then you get a system that's kind of scatterbrained. Like it just jumped from one thing to another, to another, to another, and won't focus on anything for a while. And that's because other mind agents, they use the STI to choose which atoms to pay attention to. So then what is in the attentional focus actually makes a big difference. And this is one of the more sub-symbolic style aspects of OpenCog, in the sense that we're depending on activation spreading like in a attractor neural network. And I think this aspect is fairly critical, because logic engines and anything like that tend to be very susceptible to combinatorial explosion, where it's just too hard to decide what inference path to take. And what this does is it tries to tell you what's important. And then so if you have importance spreading around, and at the same time you have a chain of logical inference going on, if the chain of logical inference at that time is preferentially choosing logical premises that are here in the attentional focus, it doesn't prove it's going to be intelligent, but it's a totally different kind of dynamic outside the logic that is helping to guide what the logic system is doing. And of course, if you have some attractor, some collection of nodes and links that are habitually activated together, then that attractor will tend to get pulled into attentional focus all at once. So let's say you have a bunch of nodes and links to do with your mom and dad, which they may not be like a well-articulated set of beliefs. They're just a bunch of behaviors you have, a bunch of things you tend to think when you're around your mom and dad, things you tend to think about. When your mom and dad get pulled into the attentional focus, these other things that are heavily linked are likely to get pulled in as well. So if you have a network of nodes interlinked by Hebbian links, they will tend to all become important at once. And then when some of them get kicked out, they might all become unimportant at once. Right? Yeah, so the basic dynamic is that STI spreads to other atoms. I mean, in practice, what the code does, it builds a big kind of diffusion matrix, like a Markov matrix from the Hebbian and inverse Hebbian links. You just kind of multiply that matrix to figure out how things are spreading. And somewhat like activation spreading in neural networks. So, as well as a way of allocating attention, we can think of this as a kind of associative memory, which is similar to a Hopfield network. I mean, if you look at the original papers of John Hopfield on Hopfield nets, he was using them to memorize images of different characters and so forth. He made a bunch of neurons laid out in a two-dimensional array. Yeah, the classic Hopfield network was a fully connected network, but it was typically visualized in a 2D array. So just imagine every node is connected to every other node by some connection of some weight, because I don't want to draw all those networks. And then let's say you want to imprint an image on it. Say you want to imprint the picture of a plus sign on it. Then you would say, okay, we will stimulate these nodes. But when you stimulate these nodes, what happens is you get excitatory positive connections between all the nodes that are marked with an X, and inhibitory connections between those nodes and all the other ones. And so then in some sense that picture has been imprinted on the network. Now, if you then wanted to imprint a different picture, say an X on it, then you stimulate a certain set of nodes. You stimulate the ones along the diagonals. The elements of that new picture get the links between them get their link weights boosted. The links between the ones in the X and the other things get their link weights decremented. And then on the connection matrix of the overall fully connected network has gotten this X imprinted on it. And you can do that with a bunch of different memories. And then what they mean by associative memory is if you put in, say, that, which is comparable to putting in a partial shape like that, what will happen is when activation spreads through the network, the other parts of the plus pattern will become active. So you'll get pattern completion, where the connection matrix of the whole thing filled in these other parts. And that's a classic Hopfield net associative memory, where you imprinted a pattern on the network. You imprint a bunch of patterns in the network. And then when you expose the network to part of the pattern, it will then grow into the rest. And so in a Hopfield network with n neurons fully connected, you can teach it like 0.14n patterns, which actually there's some math theory. You can derive where that number comes from, which is kind of cool. And if you have a sparsely connected Hopfield network, rather than fully connected one, it goes down to like 0.02n or something. So in 100 neurons, you could store 2 patterns on average, which is a little less impressive. Right? So then, the economic associative memory network in OpenCog has a fairly similar property. So I mean, it's different math equations because it's based on these rent and wages. But ultimately, it comes down to the same thing. If you have some collection of OpenCog atoms that are commonly stimulated together, then you can stimulate just a few of them and the rest will become active. It has that same property of pattern completion. So as in the example of if there's a whole bunch of atoms related to your mom and dad, you may need only to think about your mom and all those other things will get active because they all kind of reinforce each other. Oops. Thought we had more details on that there, but it seems not. Nope. Yeah, we did some nice tests on that, but I don't seem to have pictures of those ready, so we'll save them for Monday or something. Right? So yeah, is attention allocation. So any questions or discussion on this topic? I know this is something that Era does a lot with. It is allocation of attention also.
Probably concerning the role of the so-called central bank. The central bank will always be working in order to ensure that the law of conservation of currency is kept.
Yes.
Without any exception.
Yeah, the law of conservation is kept. I mean, in theory, you could make a central bank that created new money and put it into the economy, like real central banks do. I mean, we haven't done that in the code, but you could do that. Huh? I mean, for example, yeah, I mean, if you got a huge amount of new knowledge, like you imported some huge database into the atom space or something, you could decide to make new money, but there's not really much point to it, I guess. Huh?
What about it? Just like human bank decided to print more US dollars?
You could do that, yeah. I mean that we don't see a need for doing that in this kind of system. You know? Huh? It's just a theoretical possibility.
But from technical perspective, in that system, I do not see such a central bank. So
in the brain, you mean?
No, in ours.
In NARS.
Pei did not design such a central bank, so far as I know.
No, I don't think so. But I mean, Pei doesn't have this whole nonlinear attention allocation type dynamic in his system, really.
Attention in another way.
Yeah.
But maybe if you have a central bank to precisely control the whole total amount of the money, it would be technically feasible to control the cost of it.
Well, that's basically was my motivation is by making the total amount of money conserved, it's easy to monitor and understand what's going on in the system. And it was easier to do the mathematics about how the system works. But it sort of ties into the probabilistic underpinning of OpenCog, though, because in OpenCog, the short-term and long-term importance values, the semantics is grounded in probabilities. Like, what's the probability it's going to be useful to think about this in the near future? What's the probability it's going to be useful to have this in memory in the long-term future? And then going from these probabilities to currency values is kind of straightforward, right? Just as in regular economics, probability theory is everywhere. So I think if you don't have that probabilistic grounding, it's not that natural to map things into a currency either. But I think having the total amount of short-term importance and long-term importance conserved, I see that more as a convenience than as an absolute necessity for the AI system. I mean, you could just spread around neural net activation. It's probably not going to do any harm. It's just asymmetric Hopfield networks are hard to control. Like They can get into all kinds of crazy states, whereas adjusting the behavior of this sort of network by changing the parameters is easier. And that's important because the system needs to auto-adapt its parameters, right? Like, say the amount by which the rent increases when you go into the short term, into the attentional focus. That parameter maybe can't be constant over all the years that an AGI system operates. So it's nice to have a dynamical system where the behavior depends somewhat smoothly and sensibly on the parameters. And the conservative network has that property more so than the classic attractor neural network.
If I understand correctly, then first each of the processes pay their dues to the central bank, and then the central bank knows.
No, each atom pays its dues to the central bank.
That's what I meant. And then the central bank knows how much STI it has to redistribute, basically. This seems to put an upper limit on the amount of change that you can have from one moment to the next in STI distribution.
But there's a lot of atoms, you know. So I mean, yeah, it's true. The amount of money that the central bank has to distribute is limited by the amount of rent that it has collected.
And
Yeah.
if this amount of rent is a low percentage of the amount that's going around.
No, but I mean every atom must pay rent. So there's a notion of a cognitive cycle, where basically every mind in a single cognitive cycle, every mind agent is looped through, and so every cognitive cycle, in principle, each atom owes a certain amount of rent. But in practice, it may only be collected every n cognitive cycles, just because it's expensive to loop through everything. So.
Okay, so it would not be a problem if something really important happens somewhere in the other part of the atom space due to some perception or something. I don't know. Would it take a long time to get it into the focus and the rest out?
We've never seen that problem. It's been more the opposite problem of jerking its attention around too much. I mean, if something like that did happen, then the central bank could do two things, right? So let's say, you're thinking really hard about some math problems, and then a tiger runs up in front of you, right? And so you want to pay a lot of attention to that tiger, more so than you would get from charging rent. Now, there's two things that you could do as a central banker, right? You could do like the U.S. bank and print new money. So, okay, this tiger merits an economic stimulus package, right? Or you could do like the Brazilian bank used to do and take everyone's money. Say, well, I'm charging an extra anti-tiger prevention fee and charge extra rent from everyone, take that away, and then just allocate that to the nodes that will be useful for running away from or killing the tiger. So, I mean, the central bank, I mean, the economy is a metaphor, but actually the central bank has absolute power, right?
Right. I was just wondering if it might be easier or maybe more flexible to just spread activation basically as you see fit, and not worry about the upper limit. Keep track of how much STI you've divided among everything, and then just divide like that.
We did that first. It is more of a pain. So
Okay.
It's just the dynamics are hard to control, and it tends to go crazy more. So, I mean, originally, a long time ago, we had neural net style activation in the system, and it's just more difficult to predict when you tweak the parameters of the update equations how that's going to affect the overall network. So I'm not sure theoretically exactly why that's true, but that was my intuition, which was borne out by playing with the equations anyway. So that was kind of where we started.
Is the STI value divisible endlessly?
Well, it's a double. So I mean, you get down eventually to where you can. Actually, no, I think it may be just a float. Yeah.
Do you see a typical distribution of STI value against number of atoms that have a portion of that?
Power law. There's a lot. I mean, but that's controlled by the parameters, really. I mean, typically there's a few very important things and a lot of very unimportant things. Yeah. But I mean, you could tune that by tweaking the parameters of the update equations, I think. And also, in principle, that's going to depend on what the system is doing. Like a brain in a vat might have a different distribution than a system that's carrying out goal-oriented activities in the world. I mean, yeah, like if you're floating in a sensory deprivation chamber, your mind may wander a great deal, right?
If you're meditating.
Yeah, no, then you just, mind is thinking of nothing, right? So, yeah.
Another question?
Yeah, for the sake of concurrency, would it make sense to have like a decentralized currency? I know something like Bitcoin or something like that. This would also complicate the problem.
Well, it's not our problem at the moment. So, I mean, I think right now we have an atom space running on one machine. And so that's not really an issue. If you had a big atom space which is running on 10,000 different machines all networked together, which I hope we'll get to eventually, then you'd be right. Then maintaining the constant value would require coordination of all these different machines, which would be a pain. But then you could deal with that in a host of different ways, right? Because you could have each machine maintain conservation within itself, and then every now and then each machine just like reprices the funds of everyone inside its own machine. Since each machine central bank is in effect a dictator, and the nodes aren't allowed to revolt and overthrow it, right? So you could deal with it in simple ways like that, or you could have a funkier distributed currency. Yeah.
Just like because the central bank would be like a bottleneck in some way.
Right now, the only slow thing about this is iterating through all the atoms to update their STI values, right? Yeah, that is. However, ultimately, if you want to choose what to forget or what to pay attention to, you have to iterate through everything at some point. Because if you've chosen not to iterate through something, then how will it ever get the STI value to make it more important, right? I mean, you have to pay attention to the unimportant things now and then, to some of them, to check if you should boost them to make them more important. But yeah, I agree with your intuition that when we move to like a large distributed OpenCog, as I hope we will eventually, then the details of this money allocation system will probably need to be changed. And I think that's kind of a plus of the economic metaphor, because there's a lot of knowledge and intuition about economics and how to manage money in banks. You can kind of, it gives you a fairly clear idea of what to do. Like, I mean, you just use an analog of Bitcoin, right? Now we don't need the crypto aspect of Bitcoin because these nodes aren't trying to outsmart each other, right? But some of the aspects of that could be valuable. Yeah.
Just about the whole was there is no central bank for all countries. So that's
Well, then the world economic system is really fucked up. We don't necessarily want to emulate the world economic system inside we have these weird financial crises, and then different countries hold each other hostage by having large amounts of each other's money in the bank. I mean, yeah, I'm not sure. I think the idea of money and currency as a model for attention allocation, I like that, and I borrowed that in large part from Eric Baum, actually. So I don't know if you guys know Eric Baum's book, What is Thought? That's a quite good book on AGI. I mean, I only agree with about 2/3 of it, but it's well written, and it's he champions the idea that intelligence is mostly about compression, without really studying the roots of that idea in Solomonoff induction and Marcus Huder's work and so forth. But in addition to championing the idea of intelligence as compression, he looks a lot at the role of currencies for measuring and passing around utility.
Could you spell his name?
B-A-U-M. Yeah, not B-O-M-B. B-A-U-M. Eric Baum, what is thought? Yeah, but he showed that in certain kinds of learning systems, you could get a lot of self-organizing intelligence just by having little agents cooperate together and spread credit around as money, basically. So you know what the assignment of credit problem is? So this is a big problem in psychology. It's like, you know, let's say I do something of value to me. Like I pick up this cup and I drink it. Okay, well, how is the credit for that great success of quenching my thirst propagated through my mind, right? I mean, the process that actually picked this up to pour it in my mouth obviously gets credit. But then how do I know to give credit to the process that caused me to buy this an hour and a half ago? Or the process that caused me to get some money from a cash machine that would enable me to buy this, that would enable me to do that. So how do you propagate the credit backwards to all the actions that indirectly enable the action you're going to take? That assignment of credit problem has proved difficult for many AI algorithms and difficult for psychologists to see what happens in the brain. So Eric Baum showed by building some prototype AI systems, including one called Hayek, Hayek, named after the famous classical liberal economist, I guess. So his Hayek system showed that you could get interesting intelligence among a community of small independent agents by having them cooperate and then pass credit among each other using a kind of virtual money. Now his system for dealing with money was way more complex because they were like auctioning off things among each other and so forth. The way we deal with money in OpenCog is a bit simpler, but his work was quite interesting and was part of the inspiration for moving from neural net type activation to artificial money that acts a lot like neural net type activation.
Can you say a little bit more about the long-term importance and why it's important to have the same amount of it all the time?
Well, you just need the equations spreading around long-term importance have a similar character to the equations spreading around short-term importance, right? So if something is important in the long term, other things associated with it have some likelihood of being important in the long term. So you have the same kind of dynamic you have for short-term importance. It's just unfolds on a much slower time scale, basically. And then when something gets too low of a long-term importance, you kick it out. So yeah, we tossed around a lot of different equations for the updating of these things. And definitely the short-term importance equations are fussier to tune because these are things that are happening faster. And you could probably get away with a wider variety of equations for long-term importance. Right? But it's simpler just to use the same equation.
Yeah, I would just think that for the long-term importance, it's basically about forgetting, right? So it's low enough that you can forget it. That is basically
Here's the thing: if you're looking at the importance as the probability that thinking about this thing is useful over a certain period of time, I mean, depending on how you manage the utility in that calculation, it can kind of come out conserved anyway, just because if you assume there's only so much utility to go around, then the fact that there's only a certain amount of utility will lead to that anyway. So it kind of depends on what assumptions you make about utility and reinforcement and so forth.
Because if it was just about forgetting, I would assume that it's more important to look just at how how much room do I have in memory, and then forget whatever is lowest and not care about the actual amount of long-term.
Well, but how do you determine what's lowest? I mean,
Well, of course you have to have a score, but it doesn't have to add up to any specific number, I think.
no, it doesn't. It's just a matter of tuning the equations for propagating the long-term importance values, because if that gets into a pathological dynamic, you'll also have a problem.
Right.
So,
Well, real quick, for more questions. Is anybody having problems with getting the server started or being able to connect to it or getting even just OpenCog on their system?
I'm not really into this, but my robot is coming up, and then he's looking at the blocks, and then he's going away.
Oh, he's moving away from the
No,
box?
he's just back.
Did you check Under the World? Okay. You might be falling through the world.
I have that problem all the time.
Yeah. Let me double check to make sure you started the server correctly. But is there anybody that still needs the USB first?
Yeah.
Yeah.
I want to fall through the world.
Some things are easier to check with the Unity editor, but since you aren't doing this in Ubuntu, so.
Well, we have philosophers here. They can tell us where we go when we fall through the world. I've always wondered about that. Yeah.
Medieval
So
documents
that's to run how to play.
Yeah, that's true. That'll be the classical answer. Yeah. Well, then there's the idea that we're sitting on the back of a giant turtle, right? So maybe you just get to the turtle. Yeah.
It's a big ass turtle.
Well, my son had the idea that after a few million turtles, there was an enchilada. And then after that, it was enchiladas all the way down, actually.
Refer to the 1.4.6.1 boost package, just remove them and then it works on your own.
Okay. That's good to know. So what I'm going to do is I'm going to talk to Alex some more. We'll coordinate so that if we can get a version out for Monday, we'll have a new, slightly better version for you guys to tinker around with and play with. And that's when I'll go through the fuller tutorial as well. The first thing on Monday, we'll make sure everybody's set up so that they're in a good state. And I'll try to aim as much of that discussion for non-programmers as well, since there's still a fair amount of things you can do on the Unity side. If you're interested in OpenCog, but you don't want to jump in the deep end and look at this.
Instead, you want to jump off the deep end?
Off the deep end. Okay. Let's get back to it. Oh, and where's the other USB?
All right. So this will be the last portion of my own personal overviewing of technical OpenCog material. I'm going to talk about the Moses program learning algorithm. Now, on Monday, I'm going to give more of a sort of high-level philosophical overview of what OpenCog is and why, because I haven't really done that. I've given a pretty in-depth computer sciencey technical view instead of kind of starting from the highest level. So I'll try to integrate everything, and then Lake will go over the embodiment stuff, which we've been doing for controlling game characters, with some demonstrations and hopefully working out the kinks of getting that to work. And Ray Ting will talk about and demonstrate the natural language processing stuff. And I think that most likely that shouldn't take all day on Monday. So we should have a couple of hours at the end of the day, Monday, for sort of open discussion about OpenCog and AI and digging into whatever topics people want more depth on. So what I'm going to talk about now is the part of OpenCog that I have personally been doing the most with in the last couple years. I mean, I came up with the original architecture, and pretty much every component has a lot of my hand in the algorithms and ideas. Although I haven't coded much for years now. Actually, I mean, there probably are still some lines of my code in OpenCog somewhere, and probably they should be removed if so. But by and large, my role has been kind of designing the algorithms and tests and half-heartedly attempting to manage people. So Moses, I haven't coded much in either, but I've run a bunch of tests, and I've been involved at a very fine-grained level because I've been using Moses in a number of different practical applications in the last few years. And I think at this point, it's a very powerful automated program learning algorithm, but there are also some improvements that need to be made to make it better and better. And I'll give a high-level overview of how Moses works, and then talk about some of the things that we want to do to make it look better. And this presentation is kind of old. That's from the 2009 AGI Summer School, and I was too busy and/or lazy to make a new one this time. So I'm going to mostly talk and use the whiteboard, but there's some good examples in there that I'm going to fast forward to when the time comes. So first of all, let me ask, how many of you are familiar with genetic programming, GP? Well, I know you are. You're not raising your hand anyway. Yeah. So that's most people, but not quite all people. And how about genetic algorithms?
Same.
That's the same people. Okay, yeah. So the base, there's a couple people who didn't raise their hands, probably because they're not paying attention. So yeah, the basic idea of genetic algorithm, as almost all of you know, is that one way to solve a learning problem, or as it's usually put, to maximize a function. One way to solve an optimization problem is to create a population of possible solutions, evaluate all the elements of the population, see which ones work better, choose the best ones, combine pieces of the best ones with each other, mutate that combination, throw it back in the population, and then keep going. So, and that's kind of like how breeding works, right? It's like how evolution works. I mean, it's more like artificial selection than natural selection. It's like what a breeder does if they want to breed a dog that runs faster or something. You take 1,000 dogs, see how fast they run, take the ones that runs fastest, you mate them with each other, their genetic material then crosses over and mutates, then you get a bunch of new dogs, you see which ones run faster, and keep going, and that works quite well. I mean, that's how we appear to have been created, and it's how breeders have created all manner of animals and plants doing all sorts of things. So why not use it for learning as well? Now, genetic programming is the application of this to learning programs. Typically, you represent a program as a tree, where the inputs to the program are the leaves of the tree, and the internal nodes of the tree are the program operations. And then you can do the mutation and crossover by, okay, here are, well, these are all complicated. Okay, here just for extremely simple examples, this is a very, very simple program which carries out a Boolean operation, right? It has two inputs, x and y, and it then operates on them using those operators. And I'd hope to find a graph of that as a tree, but it doesn't seem to be in here. So that's sort of like it, but it has more complicated things in it. Yeah, so I mean, this is the basic idea, but it has more things I didn't want to explain yet. The inputs to the tree are the leaves. The internal nodes of the tree are the operations that it carries out. And you can represent any program you want as a tree. Of course, and or not are not the only things you would need at the internal nodes. You can put and or not, you can put while loop, a while, a for, and if. You can put various combinatory logic operations. You can put plus, times, divides, and so forth. Now, I'll explain what the particulars are here in a little bit, but the basic idea of genetic programming is you have a program represented as a tree, and then you have some fitness function which tells you what the program is supposed to do. So you feed the inputs to the leaf nodes of the tree. You get some output from the top of the tree. So then you know what you want the tree, the program to do, but you don't know what tree is going to do the thing you want. So what do? You make like, 10,000 or 100,000 trees, evaluate each of them, see which ones come closest to doing what you want. Then from the ones that came closest to doing what you want, you take parts of one, parts of another, piece them together to get new trees, mess with some nodes at random. Then you have a new tree, try it out to see what it does, see if it does something close to what you want, take the best ones, and just keep going over and over and over again. Now, this is a really hard way to write a program like Microsoft Word or Ubuntu Linux, right? It's going to take a very long time. On the other hand, if you're trying to evolve a program tree with a dozen nodes or something, then it can work okay, but it's not awesome. I mean, the advantage of this sort of approach, the advantage is that it's general purpose, right? I mean, any fitness function, any specification you have, you can apply this methodology. It doesn't require domain knowledge. The disadvantage is it can be really, really slow and require a humongous amount of computational resources. So, some people hate genetic algorithms and genetic programming. Some people love them, just like with any algorithm or other focus of religious enthusiasm. But I like genetic programming in GAs, but I realized I didn't work well enough for everything we wanted to do. And if you want to learn larger and more complex programs, or learn programs to do more difficult things, then GP either doesn't work or requires massive amounts of computing power. So in moving from GP to Moses, we made a bunch of different changes, and I'll talk about each of those. So we introduced program normalization. I'll explain that. So basically that means that a program tree is rewritten by a set of logical rewrite rules into a hierarchical normal form. So if those of you who studied computer science, they remember things like conjunctive normal form and disjunctive normal form. Actually, how many people know what those are? Okay. What's that? Yeah. Basically, a conjunctive normal form, you just take a Boolean logic expression and you put it into a conjunction of disjunctions. Disjunctive normal form, you put it into a disjunction of conjunctions, right? And so there's something else which is less well known called the elegant normal form, where you basically take a Boolean expression and you rearrange it into a hierarchical tree, with like a layer of ands, a layer of ors, a layer of ands, a layer of ors, and so forth. And the beauty of turning into, with some of the links and they have knots on them, the beauty of turning a Boolean function into an and/or tree like that is if the Boolean expression had some hierarchical structure that retains it, rather than spreading it out into a big, long, ugly thing. And you can extend the idea beyond Boolean functions to arithmetic functions, to programs with conditionals and loops and so forth. So you can take an arbitrary program and you can normalize it into a kind of elegant, hierarchical, standardized format, which sounds really boring, but it's quite useful if you think about, say, crossover, right? You're doing crossover in genetic programming, so say you have two different program trees. Well, okay, when I cross over these program trees, I might say, okay, I'm going to take this half of this program tree and this half of this program tree to make a new program tree, right? So I'll take this bit from mom and this bit from dad and put them together to get baby program, right? But the problem with that is, in general, the program trees could be just mixed up randomly like anything. So how do we know that this half of mom and this half of dad are trying to do remotely the same thing? Or this half of mom and this half of dad? We don't, right? So, and if you don't know that, what sense does crossover make? All it's doing is kind of randomizing things in a certain way. Whereas if you have put your program trees in a standardized, normalized form, then what you find is that the same parts of the same program trees tend to be doing the same thing. And we phrase that as syntax to semantics correlation. By syntax, you mean the structure of the program tree. By semantics, you mean the behavior of the program tree. And this was in the PhD thesis of Moshe Lux from 2006, which, if you look at his website, metacog.org, you can find his dissertation. The version of Moses described in his dissertation is quite old and doesn't have nearly everything the current version has in it. It's not, but it explains this point pretty well. So what we found is that if you look at the correlation between the structure of a program and what the program does, by putting a program in a hierarchical normal form, you can make that correlation much higher. So in particular, you measure that by looking at two distance measures. One distance measure is how similar are two programs on the code level. How similar do they look? Another measure of distance between programs is how similar are two programs on the behavior level. How similar is what they do? What you would like is the similarity based on what programs look like and the similarity based on what programs do to be well correlated. So when two programs look similar, they do similar things. When two programs look different, they do different things. And what we found is that is roughly true if you hierarchically normalize the program trees, and is not remotely true if you don't. And so that was the main point in Moshe Lux's thesis, which was called competent program learning. And that's one idea underlying Moses, which is a useful one. I think that's kind of the start to doing sensible evolutionary program learning, because without that, the syntactic structure of the program doesn't tell you anything about what the program does, and you're essentially just doing a random search on program space. You're kind of focused. What genetic programming is doing, in my view, is pretty much a focused Monte Carlo search. It's like randomly searching program space, and then the randomness gets a little less crazy as you get near the answer. But it's nothing more or less than that, because the crossover itself has nothing to do with the program's semantics. So another thing we introduced is demes, which are a lot like islands in genetic programming. So what that means is instead of trying to evolve one huge population of programs, we evolve a bunch of small subpopulations of programs, which are called demes. And within each deme, all the programs are pretty similar, and you're kind of fine-tuning. And then the broader search is among demes. And the conceptual and mathematical motivation for this is that the correlation between program syntax and program behavior only holds in a quite localized region of program space. So if you're in a fairly small region of program space among programs that are kind of similar to each other, and you have normalized programs, then you can say that syntactically similar programs are broadly going to be also the same as behaviorally similar programs. But that only holds within a fairly small region of program space. Therefore, you should take your population and divide it into small demes, which are regions of program space small enough that within that region of program space you have a reasonably high syntax-semantics correlation. So that's another key idea. Now, another idea is to augment the mutation in crossover with probability modeling. And this touches on the area that's called EDAs, or estimation of distribution algorithms. So the way I like to analogize this is imagine that the fine government of your country decided to outlaw sexual reproduction altogether. So they said no more sexual reproduction to produce babies. It's just too uncertain. Instead, what we're going to do, we're going to sequence everyone's DNA. We're going to decide which 10% of the population we like better. Then we're going to build a probability model of what makes that 10% of the population have good DNA. And we're going to synthesize new DNA sequences from that probability model, then make test tube babies. Then we'll see how they are. We'll take the best 10% overall, sequence their DNA, and generate new DNA sequences by instance generation from the distribution describing the DNA of good babies, and just keep going. Now, in a sense, this is what crossover is trying to do, right? It's trying to basically sample from the distribution of what makes good organisms good. But you could say crossover is very inefficient. I mean, this is the basic idea of eugenics, not to copy necessarily exactly the good people, right? You want to find what patterns characterize the DNA of the good people, what makes them good, then make new babies with those characteristics. And of course, we don't quite have the biology technology to do that with human beings yet, or someone probably would have tried. But biology isn't too far off. But in a computer algorithm, you can do that perfectly well. And that is the line of thinking underlying the branch of evolutionary learning called EDAs, or estimation of distribution algorithms. The probably most robust of these is BOA, the Bayesian optimization algorithm, developed in Martin Pelikan's PhD thesis, and he has a book on that as well. So actually in Moshe's thesis, which you find at metacog.org, he replaces mutation and crossover altogether with probability modeling of program space. Now, we put crossover back because it actually was useful. And in fact, in the current version of Moses, I think it's only mutation and crossover, and the probability modeling is disabled. But it actually adds some use. It's still there in the code base. It's just disabled by default. So actually, one thing I'm looking at now to do in the next 6 months or so is put a different kind of probability modeling in there based on a branch of math called information geometry that I think will work better than the previous kind, which I'm not going to try to explain now because information geometry itself is complicated. Although if you don't know it and you know math, it's kind of cool. It's the information geometry. It's basically the theory of how to measure distance between probability distributions. It's the differential geometry of probability distribution space, which is quite a beautiful branch of math, largely developed by Amari and some other Japanese guys. And I think we can use that to do the probability modeling here better, but that's the idea, to do some probability modeling instead of just mutation and crossover, I think is valuable. And then an idea that has been introduced recently into Moses, we have been searching feature space we're searching feature space on the meta population, the Deem level. So within each Deem you have a population of guesses, and then the collection of Deems is the meta population. So one thing we've done recently is each Deem uses a different set of features. So where the features are the inputs to the programs. So if you have any experience with machine learning, you know that, say for a problem like text classification, so take the problem of figure out which emails are, well actually that's a bad example for this audience, so hold on. Let me think of something that's not about terrorists. Hold on. Yeah, let's say you're classifying emails for someone and you want to figure out which emails are work-related and which ones are friend-related, right? The classical way to do that in supervised learning is represent each email as a vector of words, the words that occurred in the email, what's called a bag of words model. Then train some supervised learning algorithm to learn a pattern of which word vectors correspond to friend emails, which word vectors correspond to work emails. So if you had a couple hundred examples of friend emails, a couple hundred examples of work emails, and you represent each email by a vector representing the word occurrences, a supervised learning algorithm could be used to learn a model of what distinguishes a friend email from a work email. And Moses could do that too. In that case, the inputs to your little program tree are basically occurrences of words. You'd have an input for, is beer in there? Is paperwork in there? You'd have an input node for each possible word. The program tree combines the words. Like, well, if it mentions beer and wine and girls, but doesn't mention paperwork or money, then it's probably a friend email, blah, blah, blah. And then the output would be, say, a 1 for a friend email, a 0 for a work email. So in that kind of application, the problem you typically have is there's too many features. There may be tens of thousands of words that could be used as input for your classifier. And in a biology classification example, where you're trying to predict who has cancer based on their DNA, you have 25,000 genes. And most machine learning algorithms don't want 25,000 genes as their inputs. So typically you do feature selection. So you'd say, well, let's take the 500 words where the frequency differs most between two categories. Like, what are the 500 words so that the frequency differs most between work emails and friend emails? What are the 500 genes whose expression differs most between cancer patients and non-cancer patients? And that's feature selection. So you're doing that statistics-based feature selection to get a minimal feature set, which you then feed into your machine learning algorithm. And the same thing came up in more AGI-ish uses of Moses. So we were using Moses to try to learn procedures for a virtual dog to play fetch in a game world, for example. And there's a lot of actions the dog could take. And the system could search around a while, like, I don't know, just saying different things or something, barking in different ways. It's not going to help it play fetch at all. So you can restrict it, say, well, look for combinations of these 20 possible actions. and then has a smaller search space to find a program tree that will let it go get a stick and bring it back. The problem is, so much of the intelligence then goes into the feature selection phase. So that it's like all the smarts is really going into choosing what features to look at. Then the machine learning algorithm, it's figuring out how to combine this small set of features that you chose by your domain savvy intelligence, right? So in a deep learning architecture like Destin that we talked about earlier, you try to get rid of feature selection by, in essence, having the lowest levels of the hierarchy are doing feature selection and feature abstraction. So in Moses, we do it a little differently. What I did was each subpopulation, each deem. So if you have like 1,000 deems, and each deem has 1,000 programs in it, then you're searching through 1,000,000 programs at a time, which is quite feasible given the amount of RAM we have now. Each of those 1,000 deems may be looking at a subset of your total pool of features. So you have one like master feature pool, which could be all the words in English, or all the genes in the human genome, or all the actions and perceptions that your virtual agent has. You have one master feature pool. But then each deem, each subpopulation of little programs uses some subset of the master feature pool. Then when a deem goes a while and doesn't evolve any good programs inside it, you kill the deem. On the other hand, when a deem goes a while and generates some good programs, you split the deem. When you split a deem into more than one deem, then the child deem gets a new set of features which is inspired by but not identical to the features of the parent deem. So the parent deem will have some features that are more important than others, which you can judge by how often they're used and how sensitively the best programs depend on them. So you have a child deem you have a parent deem using 10 features. You may take the 6 most important features there, pass those along to the child deem. Then the child deem gets 4 other features, which are chosen as ones that have a high mutual information with those 6 good features across those cases where the programs in the parent deem are effective. So you choose new features that you guess will work well with the best features in the old deem. Add those, then you have 10 features, 6 old ones, and 4 new guesses. Those features are used in the child deem. And then you do learning with 1,000 programs in the child deem. So search on the deem level is in effect searching feature subset space. While within each deem, you're then searching program space using the features associated with the deem. And that has worked really well. I mean, we introduced that in the last year, using that on text classification, on genomics, on various other data mining problems we've done commercially for various customers. I mean, that works nicely. I mean, it uses a lot of computer time, but we have a lot of computer time, so that's okay. And the other thing, adding on to that, which we did in can't read down there, but the other thing that we did in a contract for, actually I guess a grant for IARPA, a U.S. funding agency, feature meta-learning. So what that means is if you run many different learning problems and you have 2 learning problems that are kind of similar, chances are the features that are useful for one will also be useful for another. So for example, if you're trying to learn a model that predicts whether a web page is about cats, and you next want to predict whether a web page is about dogs, you might as well start by paying attention to the features that helped you identify cat web pages. They're not going to be the same as dog web pages, but they're a reasonably good initial condition for searching for features that are useful as inputs to programs identifying dog web pages. So if you've solved a lot of different program learning problems, and you keep a database of what problems you solved, what was the goal, what features were useful, then when you get a new problem, you can find other similar problems and then try the features that were useful for those similar problems. And that can accelerate learning quite significantly, as we found. I mean, what we found is in some cases it would just accelerate the learning quite dramatically, and it almost never hurt. So that's, in general, meta-learning in AI refers to learning how to learn. It's quite broad. There's a whole field of meta-learning within machine learning, a lot of which is how do you choose what algorithm to use for a problem. But here we chose to do meta-learning on the feature selection level because one thing, I've done a lot of applied machine learning work, kind of in parallel to my AI work, mostly because I left academia a long time ago and I have to get paid, so people will pay you to analyze their data sets. So I've done a lot of just applying machine learning algorithms to data sets to serve practical purposes for various customers. And one thing you find is that although Moses was a good algorithm, like SVM is also a good algorithm for analyzing data. There's a lot of good algorithms, and it doesn't even matter that much what algorithm you use in many cases. What matters is that when you've worked in a certain domain, like genomics or text classification, or analyzing, say, surveillance data, whatever it is, you get a lot of knowledge about how to engineer the features and how to select the features. And that's more important than the learning algorithm itself. And so that motivated us figuring out how to automate more and more of feature selection and feature meta-learning. Now, the feature space search is integrated into the Moses code base. It's just part of Moses now. I mean, you can enable or disable that. It's one of the 100 command line options of Moses. The feature meta-learning, actually, we did as a prototype, and that was implemented using an inefficient collection of text files to store all the instances. So that's not been integrated into the main Moses database yet, but it should be, and actually we could integrate, I would rather integrate that using the atom space, just rather than the crude collection of text files that we used for it. Just store information about the different learning problems you've solved using the atom space. Now, how to measure the distance between two learning problems is an interesting question as well. Right? I mean, if this gets back to information geometry, if you can represent a learning problem as a probability distribution, you can use the Fisher metric to measure the distance between them. So this is all, I think, very powerful. Now, what's missing from this framework? So far, all of this works well only for simple programs. And the program normalization we implemented for for loops, if statements, while, and then arithmetic and Boolean functions. We haven't implemented it for recursion or local variables yet. So to get the full generality of programs, we need to basically add more logic rules to the reduct engine, which is what the software is called in this program normalization. That's not extremely hard for someone with a good knowledge of template programming in C++ and of combinatory logic and other techniques used inside functional programming interpreters. But there are not many people with that combination of knowledge who feel like doing this, so it's been on the to-do list for a long time. I mean, the Reduct, the program normalization code, is a pretty good program tree rewrite engine using all kinds of nice template meta-programming in C++. And inside functional programming, like inside a Haskell interpreter, they do a similar kind of rewriting. So it's not that hard, but it's not that hard in the sense that it's difficult computer science rather than like blue sky AI research. But still, that's work to make the normalization work for recursion or local variables. Now, that's one thing that still needs to be done. Another thing I think needs to be done is in doing this probabilistic modeling, I think we need to do more than just model the genomes. I think we need to model the phenome, as a biologist would call it, the phenotype, the behavior, which in this case is the execution trace of the program. So I think it's not enough just to model what the program looks like. I think you actually have to run the program and model the state as the program is executing. So if your program is a tree, then basically as you run the program tree, there's just going to be various interim states that can be viewed as decorating various nodes of the tree as the program tree iterates. And I think you want to model that sequence of interim states of the program in doing probabilistic modeling. So if you have 1,000 programs in a DEAM and 100 of them are good, what makes them good? Well, yeah, it could be something about the program tree, but if you kept a record of the execution trace as you ran the program, what makes that 100 programs good might be better identified by studying and probabilistic modeling the execution traces of the program trees. And I think that will be necessary to learn more complex programs. Yep.
Question, you want to model, for example, the genotype, not only the phenotype, right?
We're already modeling the genotype.
Yeah. But what about the mapping relationship between genotype and...
Well, in this case, the genotype is a program, and the phenotype is the execution trace of what the program does when you run it. So in this case, the mapping is done by running the program on the interpreter.
So that one-to-one mapping?
Not necessarily one-to-one, no. I mean, you could have multiple programs doing the same thing.
Oh, yeah.
We try to reduce that redundancy by doing the normalization, because the programs are put into a normal form. But we're not, to absolutely guarantee that all programs are one-to-one put in a normal form would be very expensive. So the program normalization process is somewhat heuristic. So it doesn't have to be one-to-one. Yeah.
If you have a problem where the fitness is most compactly represented, like the Santa Fe ant trail problem, by executing it in the context of an ant agent that does something and then finally finishes and counts up what it's achieved, you have to run every single mutation against the whole simulation?
Yeah, pretty much. Yeah. Well, you can do fitness estimation too. So this is another important thing. Is, I mean, if you can look at a program and see how a better similar program's done. If it sucks really badly, then you just won't run it. Now, we used to have, it's not in the current code base, in the Novamente cognition engine, when we were using that to control agents in Second Life, we had something called Third Life. And Third Life was like a really simple virtual world with no user interface and no frills. So if you had a simple program, before you tried it out in Second Life to see how fit it was, you would run it with the no user interface Third Life simulation. And if it really sucked, you wouldn't try it in the actual virtual world. So that's like trying something out in your mind's eye, I guess, basically. So that, I mean, we could do that now. I mean, you would look at running, say if you're trying to learn procedures to run the Unity game engine, you would just run the Unity core with all the graphics disabled and so forth, and then it could go faster.
Are you using fitness estimation currently?
Yeah, sure. Well, it is an option. Moses has an incredible, like literally 50 or 60 command line options, and tuning them for a particular application requires a lot of know-how, actually. Right? Yeah, so this was a graphical visualization of Moses from some time ago. It's still basically correct. I mean, you have a meta population with a bunch of deems, and within each deem there's an exemplar, which is a program that seeded the deem, and then the other ones are just tweaks of the exemplar within that deem. You have an optimization algorithm. In the old version of Moses, that was HBOA, which is hierarchical Bayesian optimization algorithm. Now we've reintroduced crossover and mutation, and we're working on an information geometric optimization. But that's all learning inside the deem. There's Reduct, which is the program normalization software. And then we have creation of new deems, and it all just cycles around. So you have the two levels of evolution. And part of this idea of two levels of evolution was inspired by Douglas Hofstadter. He proclaimed in one of his books that all of learning is either knob twiddling or knob creation. So if you think about like a knob is like a dial that you could turn to one level or the other, right? And at the trivial levels, like creativity, invention is just twiddling knobs. So you're changing some parameters of something. Okay, we have glasses. Let's make the glasses bigger, right? Let's turn them red. Then you're changing the size knob or the color knob or something, right? But at a more fundamental level, innovation would be about adding new knobs. Like, oh, let's add a camera, right? Adding a camera is not just adjusting some parameter. That's adding a whole new feature, right? So the basic idea is, in that metaphor, the learning inside a DEEM is knob twiddling, and learning of a new DEEM is knob creation. So inside a DEEM, you're optimizing parameters and aspects of a program, but to add a whole new aspect to a program, then you're creating a whole new DEEM. And that's kind of simplistic way to break things down, but it seems to work reasonably well. Yeah, so this kind of exemplifies that metaphor. Trivial example of a program, which is a Boolean combination. And basically, you view each thing there as a knob that can be twiddled. So this very simple program tree, X and not Y, takes two Boolean inputs, gives one Boolean output. You represent it as a tree that way. And we're going to represent each of those things as a knob that can be flipped. So AND is a knob that could be switched to AND or. Y is a knob that could be switched to not Y, for example. So you view each part of the program tree as a knob with several settings. Then the job of searching within the DEEM is basically figuring out the right knob settings. And I mean, you can extend that in various ways and look at various ways to tweak the parts of the program, but you're not going to add something fundamentally new. So within each DEEM, you start with an exemplar program, and you're looking at various small tweaks to that exemplar program. So this is the knobs for X1 and not X4. These are all the variations that the code would look at now in terms of replacing things with their negation and replacing and with or and so forth. So that's not a very large search space. Right? So then, based on the settings of those knobs in the previous slide, you can get these various simple programs. So these programs are all gotten by different knob settings, and they're all in the neighborhood of that initial program. And then you can measure the distance between those and the original program in terms of just tree edit distance. Oh, there's Moshe. Right? Oh, that's a cool combination. Yeah, I've don't have much time, and I've kind of already went over most of that. But actually, those are all Boolean examples. I want to show an example which is more virtual world-like. So this is something we have not yet reactivated in our current virtual world. In an older version of the virtual world, we were using Moses to learn behaviors. And sometime in the next months, we will reactivate that in the new game world now. I mean, there were various things irrelevant to Moses that were obsolete about the way that whole system was built, and we'll now reconnect it. Because this, I mentioned OpenPsy, which is the kind of motivational system underlying OpenCog. When we had Moses connected to the game world, we didn't have OpenPsy. We had an older and cruder method of motivation and action selection. So now we need to reintegrate Moses within the new framework with the OpenPsy for motivation and action selection. But what we were doing back then was basically learning by imitation and reinforcement. So for example, if I want to teach the virtual dog to fetch something, So I would show it examples of fetch with a human imitating the dog. So I could say, okay, now dog, we're going to learn to play fetch now. Cosmo, fetch the stick. I throw it. Cosmo would get the stick and run back. They'd say, see what Cosmo did? Now you do the same thing. That was fetch, right? And this kind of imitation reinforcement learning, I got the idea of that from the literature on how to teach parrots things, actually. Now, dogs don't tend to be taught that way that well, but parrots are very competitive and very social among each other in this particular sort of way. So if you have a parrot, you want to teach it something, do the thing with another person. The parrot watches, then it will copy that thing. And then, because parrots love to imitate, right? And that gives them a specific other student to imitate. So they know what they're copying. You still reinforce them and reward them if they did it well, of course. But by giving them something to copy, you make their learning much faster than if they just had to try random things and then get rewarded if they did it well. So we implemented that kind of learning. Actually, we did it with virtual dogs because we were working with a customer who wanted virtual dogs in Second Life at that point. I would have rather done parrots. Actually, this is why I bought a parrot. Then that company downsized as part of their operation, and we never built the virtual parrot anyway. But it inspired me to buy a parrot, which was good fun for a few years. Second Life kind of became less interesting as a business avenue, right? I mean, that was really big in 2005, 2006, and then I think when the FBI outlawed gambling in Second Life, then the popularity went downhill quickly. Right? Then all that was left was porn, and that wasn't enough to sustain it. Right? Yeah. So anyway, we use Moses. And if you look in the current OpenCog code, you'll probably still find the word pet in there in some random places, because what's now called the agent controller used to be called the pet controller because it was for controlling virtual dogs. And we're gradually de-petifying the system. So we had a special COG server, which was the operational pet controller, then renamed the operational agent controller. And that kind of stored the memory of everything that the little dog did. And then we had a separate COG server called the learning server, which ran Moses to learn programs. And then these tended to run on two different machines. We had communication between them. Now, the fitness function here, the fitness function measured basically how well did the action of the AI agent, which in this case was a little dog, how well did the AI agent's actions and the responses of the world to the actions mimic what they saw in the example. So in the example I gave, the exemplar would be Cosmo running to bring the stick back. And then if I told the dog to get the stick, it would go and get the stick back. And if it brought the stick back to me and I said, yeah, good, it would see that was the same thing that happened when the exemplar was given. So basically, in this case, it is given the phenotype and it has to learn the genotype. It's given what the program does in the world. It has to learn what the program will look like. And here, we gave it primitives like this. So sequential AND, which means do one action, then afterwards do the other. If statement, we had a separate if statement for actions. A while loop, not, choose a random object, choose the nearest object, grab, go to an object. So we had a fairly special set of primitives that were used, kind of like crafting a programming language just for little virtual dog behaviors. But I mean, that's not unlike what you do when you have to write scripts for any domain. I mean, if you're writing scripts for biology, you have primitive functions that compare gene sequences or something. So here, but there was a fair bit of artistry that went into this. There's an action, go to object. And that saves a lot of having the action be go-to coordinate in terms of making program learning simple. But in this case, Moses was given primitives for loops, conditionals, Boolean operations, and then basic actions in the world. And there were about 70 different actions it could do. I mean, some of which were like wag your tail, wiggle your ears, bark, stand on your hind legs, turn around, turn right, turn left, walk fast. In practice, each of those actions correspond to an animation coded in Maya, I guess, which were then imported into the game world, which was, in this case, the multiverse game engine, which we moved to after giving up on Second Life. And this whole modality of defining actions is kind of crappy. I mean, really, you'd like it to be controlling servo motors rather than like whole canned animations for step forward or turn right. And ultimately, I think our architecture can do that. But the game engines and virtual worlds that we have now tend to want you to supply canned animations for actions. That's the easiest thing to do in this context. So here are some programs that the system learned, like fetch the random object, like dance until the owner says stop dancing, kick 3 times from the left leg if the stick is nearer the ball, from the right leg otherwise. So, I mean, if you follow these behaviors for a while and give examples, the system will watch what you're doing, then it will learn one of these programs to emulate your behaviors. And I mean, this is a simple language, kind of like Lisp, but crafting this language was important to figure out what, I mean, you see it's grab, right? So you give it the ID of an object. Every object in the virtual world has an ID. You give it the ID of an object and you say grab that object. Now you're not saying like move this servo motor by 37 degrees, clench this finger by blah, blah, blah. You're saying grab that object. And of course, if you had a whole hierarchical actuation system, like I alluded to this morning, this kind of stuff could exist on the higher level. Because I mean, even as a human, yeah, I certainly at some level I'll say, okay, I want to grab that bottle. And that just leads you to a lot of lower level things. And in most cases, when it's a behavior that's already routinized, that hierarchical division is pretty effective. Now, if you're trying to do something you haven't done before, then the higher and lower levels have to have a lot of feedback. And you're doing some adaptation and some motor learning even while you're carrying out the action. But anyway, this sort of thing Moses could do without any problem in this context. And we also did some pure reinforcement learning without the imitation. And pure reinforcement learning works the same way. You just need a lot of trials, just randomly trying shit until it finds something that works. So. Yeah, here you see examples of similar programs which have, I mean, very minor differences, right? So there's only knob twiddling between one program and another. Like here a random object is replaced with nearest object. Here the objects are replaced with balls. And by twiddling the knobs in one program, you get another program that is related, but of course in the real world can do something quite similar. Because here you're always grabbing the nearest object, whereas here you're grabbing a ball. Here, this one doesn't work, right? You go to, or it does, you go to a random object, then you grab the random object. So that's fetch, but you're fetching a random thing. So those programs would all be in the same DEAM. They're minor variations. But if you wanted to add something totally different, you'd have to go to a different DEAM. Yeah, one thing we found in this application is, so the fitness function in Moses has 3 components now. One component is the basic score, the behavioral score, which is like what do you want the program to do. That's what you're trying to maximize. The other component is the complexity of the program. So you want to penalize programs that are too big and reward programs that are small. This is because of basic statistical learning theory, that a compact program is less likely to overfit to its training data. Then the third component is a diversity reward. If the program is different than other programs the system has learned before, you give it a fitness boost. If it's very similar to something learned before, you give it a fitness penalty. So by combining these three terms, you get programs that are good at optimizing your function over the training data. They are small, and they're different than other programs you found before. Then, in many applications, what we do is get a whole... In this case, you just need one program that you can execute, right? In, say, a classification application, you can get an ensemble of programs and vote among them. And then having a diverse ensemble is also useful for that reason. Yeah, various other programs that were learned. I wonder, see if I can find yeah, this is not that polished, but this is that's a screen capture. Then we just put thought bubbles of some of the nodes and links in the atom space at the time, just for the heck of it, but not the full atom space, obviously. So unfortunately, we didn't have a graphic artist at this time, so we just used like clip art from the web for all the characters. So all they have on the web is these stupid bimbos for characters, basically. As you see now that we have a graphic artist on our team, we got less ridiculous looking characters in the game world. So, and you Fido, learn fetch from Sally. Sally, do fetch, done fetch. So in this protocol, you actually told the agent, like, okay, I'm starting to do this behavior, I'm done with this behavior. And that makes it extremely clear. Right?
Pretty realistic.
Yeah. Me bad. Yeah, I have had dogs that do that reliably. Or they'll just get it and like run away and never come back. Good boy, yeah! All right, that's a good dog. Yeah.
I don't really get it. This little networks, this links. Is it atoms that have?
Yeah.
Oh, I see.
But those are it's kind of a cheat because those are hand-picked atoms that we just put there for the heck of it. I mean, they're not. Those were not necessarily the atoms with the highest short-term importance or something. We just picked the atoms that seem most relevant. So.
You get a credit assignment program here as well, because I mean he starts out doing something good, running to the ball, and then he does two things that are not really correct, and then he does correct things. So
you certainly could. Then you just need more training examples, basically. Yeah, that could happen. This one was more complex. It was like follow the leader. So you teach a dog to follow another one around. So, but I mean, this may be a few minutes long, so we could talk or have questions while it's going. So basically, most of the work I've been doing with Moses recently has actually been outside of OpenCog. I mean, you can use Moses together with the rest of OpenCog, or you can use it separately. And I've been I've been mainly using Moses as a machine learning algorithm to analyze various data sets. And however, the improvements made in that context are pretty general and are going to be useful for OpenCog as well as for Moses as a machine learning algorithm. For example, the main thing done in the last year is putting feature selection inside of Moses, and that's very useful for practical applications in machine learning, but also you really need that in an AGI context as well, because if you're doing something like learning how to move in a context where there's 1,000 different actions you could take, in an AGI context, there's no one selecting the 50 relevant actions of the 1,000 total ones. The AI has to do it on its own. I think to be most useful in AGI, though, we need to extend the representation language. I mean, in principle, it can deal with the recursion and local variables in the programs, but in practice, the reduct engine doesn't normalize those. And along with that, we need to extend the probabilistic modeling to model execution traces, because I think without that, I think when you start having programs that have recursion and more complex control structures, I think the correlation between the program syntax and the program behavior will break down, and you're going to have to actually look at the execution trace to measure the program behavior. And all that in a certain way is easier than a lot of other OpenCog stuff. I mean, it's hard and it's difficult programming. It involves advanced mathematics, but it's pretty much just computer science. So if you know advanced computer science, you can do that in a somewhat determinate way. It's not as much open-ended research as a lot of other things. Now, once those things are done, then there's going to be quite interesting exploration of the probabilistic modeling. Like, if you have a bunch of programs with the recursion in them and so on, and you have their execution traces modeled, exactly how do you get the probability modeling to work, to model which programs are good and which ones are bad? And I think we can do that using information geometry, but that's certainly an interesting and challenging research direction. In the overall OpenCog context, it's not quite clear how far you can go with this, because we don't know how big are the programs that you can evolve with this given tractable computer time. I mean, Moses now makes good use of multiple processors, and you can run it distributed on as many machines as you want. It distributes the model building and the Dean logic and everything. I mean, each machine has a bunch of Deans on it, basically. So, yeah, unlike the OpenCog atom space, Moses, as its separate process, can do effective distributed processing, which is a simpler problem because of the way the algorithm is. All evolutionary algorithms are easily parallelizable, right? So, even so, I mean, the population size you might need to learn complex programs with complex control logic could be infeasibly large. But the basic idea in an OpenCog context is to have Moses learn a variety of small programs, small meaning maybe up to 50 program tree nodes, and those are then entered into the atom space, and PLN learns how to chain them together and combine them together to do different things. And Moses can be used to learn procedures like we saw here for like how to do things. But it could also be used for classification. Let's say you have, say, a category of people like AGI Summer School students, right? Now, if I want to learn logical statements characterizing this category of people, one thing I could do is internally I could pose it as a supervised learning problem. I could say, let's use Moses to learn a classification rule that will distinguish AGI Summer School students from random people, right? Moses can then run that internally launched classification task. Then it will come up with an ensemble of rules that predict who's an AGI Summer School student and who isn't. those rules then become logical content in the atom space that can become reasoned on. So in essence, whenever you have some concept that seems important and you have many examples of it and you want more information about it, you can automatically have the system launch Moses to learn new logical content about that category. And the conclusions it would draw could in principle be drawn by a logic engine, but Moses is a completely different control strategy. I've been doing this evolutionary search. It's able to make large leaps that a logic engine, due to its incremental nature, isn't going to make. So I think, as well as learning procedures like that, you can use it to learn logical content, but in a more holistic way than a logic engine will do. And then a logic engine can then reason about that ongoingly. And then, of course, what the logic engine reasons about poses new links that go in the atom space that could then be used by Moses in future classification tasks, which would be another example of the principle I called cognitive synergy, where you have classification engine using logic links to learn new logic links and then feed into reasoning, which makes new links that feed into classification and so forth, which is something we have not done yet, unfortunately, but could be done perfectly well using the current state of Moses and the OpenCog code base. I mean, that's not extremely hard, but I mean, like anything else, you're running a bunch of different AI components together on a bunch of data, and you have the question of what data do you want to use. So we've been working a while toward getting the, this was all in like 2007, 2008. I haven't even looked at it for a while. Nope. We've been working for a while toward getting this new virtual world up and running, with a goal toward using the new virtual world as a platform for doing all this other cool AI stuff we want to do, because all this stuff requires a lot of data from somewhere. And where do you get the data from? I mean, you can load in data from files about various applications, but that always leads you down some narrow AI type path, it seems. If the data comes from an agent's embodied experience, it's going to be richer in various ways and better for integrating the various cognitive processes. Yeah.
When Moses learns something, it's in its own programming language, right? So if there's a bunch of rules.
Combo is what the language is called, yeah. It's like Lisp with a bad haircut.
Okay. So it's in Combo, and then it learned, for instance, a bunch of rules for classifying summer school students. Could you convert it to links?
Yeah, there's code for that.
Okay.
You can convert Combo into implication links and AND links and so forth. Yeah, we've done that. We did that in 2006 or 7 or something. I mean, it hasn't been done much lately, but the code is there. It's not difficult. Now, if we were, that's with like while loops, if statements, and so forth. If we put recursion into Combo, which it used to be, then we took it out. I mean, it used to be based on combinatory logic, which is why it's called Combo. Now it's still called Combo, but there's no combinatory logic in it anymore. But if we put that back, then there's the question of how to get your reasoning algorithms to work effectively on the atoms that you put in. It's no problem to put them in the atom space. And at the moment, I think the PLN design should work fine that way, but it all depends. Like the idea of combinatory logic is to do arbitrary abstract reasoning without variables, just by using higher order functions. And if you do that, PLN can deal with it really easily. But I'm not sure that's really the optimal way to do it. Because if you ever try to write a program with no variables, it's possible, but it's quite contorted.
No variables and because, for instance, if you write something in Haskell, then
Haskell's not pure combinatory logic. But inside the Haskell interpreter, somewhere is pure combinatory logic. After you strip out all the variables. All right, well, that is Moses. I know everyone's ready to go, but if there's any questions, I can answer them anyway.
One question. Do you think in the future you will need to integrate some other kind of machine learning techniques, like SVM?
No.
Yeah. Moses is going to
Probably not. I mean, I think that an advantage Moses has over SVM is that the rules learned are easily reasoned about. Like the program trees, you can export into downspace. They can be reasoned on by PLN. I mean, what SVM learns is some separating hypersurface. The equation that comes out of it is quite opaque. And, I mean, there's not much the other AI components are going to do with it. I mean, in point of fact, the new version of Moses seems to work better than SVM anyway, since we integrated feature selection. But I'm sure that doesn't hold on every single problem, because SVMs are very powerful too. Yeah, I mean, I came to the conclusion a while ago that the machine learning algorithm itself is not necessarily the most important thing. Like, you can put inside a Moses Deem some other machine learning algorithm, but if you're doing all the same stuff of allocating subsets of features to each Deem and all the other high-level aspects of Moses, you could probably get it to work all right. I mean, SVMs have the same problem with feature selection too. I mean, you can do recursive feature selection, but that's very, very slow with SVMs. Otherwise, when you use SVMs, you always do some statistical thing to filter down the feature set first. So I think that's a problem in an AGI context, actually. I mean, if I were going to use another machine learning algorithm, I would use like a decision forest or something, because that's quick and dirty. And, well, I mean, boosting is not an algorithm. It's a technique. You could use a boosted decision forest. The thing with a decision forest is you're learning a tree, and the tree that you learn could then be pruned and reduced and imported into the atom space and reasoned on much more easily than the separating hypersurface learned by SVM. Because, I mean, there's an argument to use something like decision forest as a preliminary to Moses, just because it's simpler. But in practice, I tried that, and it didn't really help. But that kind of thing could make sense. But the important thing here is we have to think about the interaction between different AI components, right? So having the world's best machine learning algorithm in this OpenCog context doesn't help that much unless not only the classification results, but the actual classifiers learned by that machine learning algorithm can be used as cognitive content by other learning algorithms. Because we want to get this kind of synergetic interaction between components working. You got a question? You forgot it?
How the planner works, but I don't know if that fits in.
Nobody knows. Do you know how the planner works?
The shooting plan?
Yes.
No, I don't generally know.
Do you specifically know?
No.
That would have been interesting. Yeah. I do generally know, and I don't specifically know. I mean, it's a hierarchical planning algorithm. I mean, it has some vague resemblance to graph plan, but it manages uncertainty and deals with hierarchical decomposition differently. So I mean, it is not like a super all general AGI planner. I mean, it's somewhat specialized to the kinds of plans that are going to come about in this game world. On the other hand, it has hooks where if it can't come up with a plan, it's able to pose the problem to PLN or some other learning mechanism to come up with a sub-plan, which is an advantage. If you look in the planning literature, almost none of the academic planning algorithms are scalable to the case where there's a huge amount of information. So it kind of began as an attempt to tweak graph plan, which is a classic planning algorithm, into something that would be more scalable. And there's various heuristics for decomposing a plan into subplans, into sub-subplans, which make use of the fact that most of the plans are about spatiotemporal things. So like if you're trying to make a plan involving two far distant places, you may try to make subplans involving spatial subregions or something. So it was really Xu Jing's brainstorm, and she has not yet written the document explaining how it works. So we're all looking forward to understanding the details. But that's the high level aspect, anyhow. Huh? I mean, you could. The way I would like to do planning is just to do planning as temporal inference. I mean, you can express time explicitly in the logic, and then planning is just logical reasoning, right? And there's no strong reason not to do that. I kind of hate the whole field of planning within AI. I mean, it's just extremely rigid, specialized algorithms that are not, and they can't deal well with planning in dynamic context when the situation is changing during the planning process. So Xu Jing's planner works around those problems to some extent, but in the end, it's still kind of a souped-up graph plan. So I think it will need to be replaced by something more general at some point. On the other hand, it could end up being useful for a long time as a module called by some more general inference-based approach as well. Just as you can use a navigation algorithm as a routine, like if you want to get from point A to point B, first thing you can invoke A star because that's easy. And if that tells you how to do it, just do that. Then if A star doesn't work, you can try to use reasoning. Or you can use A star to get as far as it'll go and then use reasoning and try to get the rest of the way. I mean, so and maybe we'll end up using Xu Jing's planner in that sort of way. Because it probably is going to be faster than doing planning as a subcase of temporal logic within PLN, which I think would be a more generally satisfactory way to do planning. Anyway, we may have the answer by the time you arrive in Hong Kong in a couple weeks. So she has to publish a paper on it for her PhD, so she has to write down something resembling the truth about it at some point.
I asked before about novelty preference. Do you have time to explain it to us?
Novelty?
Novelty preference.
I
asked it through.
Yeah. Well, the way we measure novelty basically is by how different is something from what's already in the atom space. So if you enter a new observation or a new thought into the atom space, then how much change does that make to the atom space? How much does it change the truth values of the things that are already? I mean, if you just observe another red apple, right? Then what does that do? You may update the strength of the apples are red link a teeny tiny bit. It doesn't really matter, right? If you observe a purple apple, well, that's a bit weird. And actually, in that case, what PLN is supposed to do, since that's so different from everything else, first of all, you create a node for a purple apple. Then you get a new link, apple inherit from purple with a certain strength there. So that's actually a change to the atom space, right? So how much does your knowledge base change when you see something is the basic idea. And you can measure that in a couple ways. You can measure that immediately, or if you had an operational PLN, you can measure it after doing a bunch of inference. Like after I think about this a little, how novel does it still seem to be? And what you find is that approximates the amount of surprise value according to information theory. Because I mean, the surprise value is about entropy, which is log probabilities, and the PLN truth values are conditional probabilities. So in essence, it's very similar to, Jürgen Schmidhuber's algorithmic theory of beauty. So Schmidhuber he's at INSEAD in Switzerland. He's one of the titans of the AI and AGI field. But he has these theories trying to explain beauty in terms of information theory. And it's a lot like surprisingness. What he argues is something is beautiful if after you see it, it lets you compress your experience much more than before. So I think it's a very simplistic theory of beauty, but it's an interesting theory of surprisingness because, I mean, compression, you can compress something if you've identified patterns in it. So if seeing something lets you compress your experience significantly more than before, then that means you've gotten some information out of it, basically. And that mathematically, these all kind of come down to the same thing.
Could you spell his name?
SCHMIDHUBER.
HUBER.
First name is JUERGEN.
But then wouldn't the purple apple not because that probably makes it harder to compress your knowledge about apples, right?
A purple apple would make it harder to compress. So the purple apple is surprising but not beautiful. And, yeah.
But I thought that this surprise, beauty, humor, etc. all was the same formula.
Well, let me think about that. So they can't be exactly the same formula. I mean, they're all different permutations of the mutual information.
Okay.
But they can't be exactly the same because, as you say, seeing a purple apple would not let you compress your experience better. It would just give you more confusing information, right? So yeah, what would be beautiful is if somehow you discover that the purple apples and the red apples were all actually green inside, and then you could somehow compress things more. Right?
When you're rewarding a program for size compactness, in addition, could you reward it for having lower logical depth in the sense that it's somewhat bigger, but it takes way less time?
You could do that. Yeah, that would make sense. Yeah, you could have runtime as part of the outcome penalty. I mean, for most of what we're doing now with Moses, we're using like Boolean functions, arithmetic functions, some conditionals. It's not going to make a big difference.
Yeah.
But if you add like some loop in there with a large loop index, that should be rated as complex as well. So yeah, true.
You mentioned that you would like to use PLN to compose programs that were invented by Moses.
Mm-hmm.
Do you need PLN? Couldn't you just get Moses to use previous programs as primitives?
You can also do that. Yeah, the main, we have done that. So I mean, you can take previously learned Moses programs and use them as modules. So I mean, in that last video that I didn't comment on, you could teach it some dances. Then those dances are like encapsulated routines, and they can learn how to do those dances based on different triggers. So, but the issue there has to do with the different ways of using prior knowledge. Like PLN, like any logic system with a large knowledge base, it's very much like a lifelong learning type system. Like everything it's ever seen is there. And how to use all that prior knowledge within Moses is a little bit trickier. I mean, you can use it in principle, you can use it inside the probabilistic modeling step, where how you probabilistically rate a program as being good depends on your prior knowledge from history rather than just what you've learned within that particular learning run. But we've thought about that a lot and haven't actually done it, how to use all the prior knowledge inside the probabilistic modeling that models the fit program. So like when you're deciding why a program is good, you may use your prior knowledge to help you figure that out. But it's not clear, while Moses can use prior knowledge in that sense, it's not clear if it will use it as well as or in all the ways that uncertain logical inference will do. But that would be the big issue there. But yeah, reusing modules certainly is necessary.
And when you make your initial teams, they get a subset of the features that you have. Is this just a random subset, or can you get from the atom space something that makes sense together? Or?
At the moment, we actually have a separate Python program that searches for good feature sets that have high mutual information with each other and with your target variable, but it kind of depends on what problem you're solving. So we use some heuristics to try to find good feature subsets, but that's kind of domain specific at the moment. So a good general way to do that, yeah, if we were doing everything fully integrated with the atom space, and if the features were atoms, then you could use the Hebbian links, for example. You could choose a bunch of atoms that had high weight Hebbian connections between them. So like a map or a cluster of activity in the atom space. And that would be a good initial seed for a gene within Moses, which is a good idea, but we haven't done that yet.
In your book, you defined structural complexity as the total amount of pattern entity. Can you describe how that works?
That's interesting. That was a version of me who was like 22 years old, I think. Let me think if I can remember that far back. Well, yeah, that's sort of out of context of all this, but the idea there was the Kolmogorov complexity defines the complexity of something as the length of the shortest program that will produce it, right? But that's kind of not what we mean by complexity in everyday life. Rather, I want a definition of complexity that would mean the total amount of pattern that some entity has, right? So you can look at all the programs that would compress some entity, and then each of those programs has a certain compression ratio. Unfortunately, those programs, and so that's in some sense a crude measure of how complex you are, is how many different compressing programs are there for you. But then you have a problem of overlap. How do you tell when two programs are partly compressing the same thing? So you can say, okay, take program 1. How much does that compress you? Take the version of you compressed by program 1. Then take program 2 and see how much would it compress that, and so forth. And then you get a series of compression ratios. But the problem is that's order dependent. So I just took the average over all possible orders, just because it was the only thing I could think of to do. I've come up with more elegant ways to do that same thing more recently. But the basic idea is to find a way to encapsulate the total amount of pattern or structure in something.
Have you published something more recently on that?
No, I didn't publish it. It's on my hard drive, I hope. Yeah.
Is it, at some point you will?
Maybe. I mean, the thing is not being an academic anymore. I have no need to publish every random thing I think of, and it's very boring writing stuff up for publication. So like 95% of the interesting things I and the OpenCog team have done, we didn't publish because no one reads. The average academic paper is read by probably, I don't know if it's less than one person because I don't know if the writer even writes it, but it was 1 point something people is what I read somewhere.
That train of thought is fairly interesting.
Yeah, it's interesting to me.
How would you represent the features in atom space? Isn't it very different from the current concept or things you stored in the atom space?
It depends on what you're doing. I mean, if let's say you were trying to classify business people versus programmers, right? Then if you had nodes for a bunch of people, I could have a Yi-Ching node, a Cosmo node, a Rei-Ting node, and so forth. And then we could have links about each of you, like he inherits from male, she inherits from Chinese, the various evaluation links, right? She likes to read this kind of thing. This person likes to talk to people a lot. So you'd have links about each person in the atom space. And then the features for Moses would just be what are the links for each person. So it'd be a link type, a target node, and a strength, right? So that's not so difficult. I mean, we did that a long time ago. I mean, we filled the atom space with information from a survey, the National Longitudinal Study of Youth or something, and then used Moses grabbing stuff from the atom space to do classification of which people were likely to be poor and which people were likely to be rich or something. So we discovered it's bad to take a lot of drugs and have a baby under the age of 15, which wasn't very profound, but it did have Moses doing classification based on data grabbed out of the atom space.
But those are very high-level features.
In that case, yeah, sure.
Do you think you'll be able to capture these low-level features?
Moses doesn't care what the features are, right? I mean, so one of the things we'll do in the next few months is using Moses on the output of Destin. And then we'll probably use lower and higher level features together. So we'll use the winning centroids at each of the higher levels of Destin, and we'll use the frequent subtrees extracted from Destin, and throw all those in as a feature vector of an image, and then use Moses for semi-supervised image classification. So, I mean, when we do genetic analysis using Moses, the features are quite low level. I mean, it's like the expression level of some gene. So there's no problem with that. The question is more, what else is going to act on that knowledge in the atom space? Because if you're just going to feed features into Moses, then you don't particularly need the atom space. The point of using the atom space would be if, say, attention allocation is going to prioritize some things that Moses will then more highly weight, or PLN is going to draw conclusions from that before it's fed into Moses. I mean, in the game world context, for example, Moses could be used in a number of ways. Say classifying good guys from bad guys would be one example, which is pertinent in video games. You have some characters who come up and do bad things that decrease your happiness. Other characters that come up and do good things that increase your happiness. What's the difference, right? So then the training data is a lot, right? It's the physical traits, how tall they are, what clothes are they wearing, what kind of blocks are they made of, but it's also the behaviors, like how fast are they running, who was near them, and so forth. And the interesting thing there is how do you select of all the nodes and links relevant to those characters, which ones to feed to Moses? I mean, do you just say, well, I'll go 2 or 3 links away from the node for each of those characters and take that whole subgraph and feed in as a feature vector? But in some ways, that's similar to problems you have in language generation. Because if you want to say something about a character, how do you choose which of the nodes or links about that character to extract and then feed to Rating's natural language generation subsystem? How do you choose the pertinent subset of the hypergraph? And that's a tricky problem, actually. That's if you have like a full-scale atom space from an agent's rich experience, trying to pick the right subset is an interesting problem. And you could look again at various information theory measures there, like how much new information is each new node giving you about the character. But it's we haven't really addressed that problem yet. All right, we are done.